Hello, I am Ronen Personas from CNRS, and I'm going to present to you Dora the Explorer, a system leveraging deep reinforcement learning for very large data exploration. This work was supervised by CIKM Maria from CNRS, and it was a collaboration with Dora CIKM from IRD and Maximilian Fabricius and Srividya Subramanian from the Max Planck Institute. It was part of a European project called iNode about open data exploration. One of the use cases of this European project was the SDSS dataset. This dataset is extremely interesting for us for data exploration as it is really huge. It's made of millions and millions of records of astronomical objects, each object being represented by hundreds of very hardly intelligible numerical attributes. So in our case, we focused on 2.6 million galaxies with the 7 attributes you see on the right. As you can see on this sample, the nature of the data itself makes its exploration and understanding very complicated. A good example of this complexity is the discovery of the green pea galaxies. The green pea galaxies are those uncommon compact galaxies looking like green dots. They were only discovered a few years ago by volunteers of the Galaxy Zoo project. The Galaxy Zoo project is a collaborative project allowing volunteers to classify galaxies based on some visual features. What's interesting in this discovery is that these galaxies with their data was present since the beginning in the SDSS dataset, but they have only been found by chance since there was no adapted exploration tool. So this brought us to the first question we try to answer in this work, which is how do we navigate within such a dataset? Our proposal is exploration pipelines. An exploration pipeline is a sequence of exploration operators closed under set-based semantics. So in Dora, all the exploration is based on item sets. An item set is defined with a conjunction of predicates. Here you can see an example of an item set in Dora, which is composed of 52 galaxies and is defined by these 4 predicates, with the redshift, which is the distance between the Earth and the galaxy, the R and G attributes that are color magnitudes, and the petrorad attribute, which is representing the compacity of the galaxy. To compose these pipelines, we defined 4 operators that are implementations of by example, which means that each operator takes an item set as input and is returning one or more item sets that are related to the input set. So here you can see descriptions of each of these operators with a visual representation where the input set is represented with a plain line and the resulting sets are represented with dotted lines. So the 2 operators on the left are bifacet and bisuperset, which are our implementations of the usual drill down and roll up operators. Bifacet splits the input set on a given attribute, and bisuperset is proposing multiple relaxation of the provided input set. Then we have added 2 operators that are offering different exploration possibilities. The first one is by neighbors, which is finding the item sets immediately above and below the input set on provided attributes. And finally by distribution, which is returning item sets that are showing the same difference between their predicate values. So let's take a look at Dora in action. This is the interface of Dora. In the operator selection, the users can pick the operator they want to execute and the attributes for this operator. Since we start the exploration on the whole dataset, we have to start by doing a bifacet to split this dataset on the provided attributes. In this case, we will use the G magnitudes. We execute the operator, and we get the resulting item sets. Here you can see that all the item sets are defined by a range of values on the G magnitude, which is the one we use for the operator. Since the the lower the value is on a color magnitude, the brightest the galaxies will be on its color range, then you can see that all the item sets with the lowest magnitude values have the brightest galaxies, while when we go to higher values item sets, the galaxies are darker. So let's pick an item set with pretty bright galaxies, and let's delve deeper into it with another bifacet. Let's do it on the petrorad attribute, which is the compacity of the galaxies. We execute the operator, and we get once again the resulting sets. In this case, we see that a lower petrorad value brings more compact galaxies than a large petrorad value with more diffuse galaxies. Let's pick a set of compact galaxies and delve deeper inside. Let's do another bifacet, this time on the R magnitude. Here we see very strange looking galaxies that are blue dots. Those are probably blueberry galaxies. We can look at neighboring sets for maybe more blueberry galaxies by doing a by neighbors on the petrorad attribute. So here we got some pretty close results with some galaxies very similar but a little less bluish. Now those two item sets are very small, so it could be interesting to get some bigger item sets. So let's execute a bi-superset on them. Finally, we might be interested into getting more variety in the results, so we can execute by distribution, which will return all the sets having the same distribution of values in their predicates. So, as you can see, these exploration pipelines and exploration operators offer many possibilities for exploration of the SDSS dataset. But it is still pretty hard to orient yourself and to know what to do actually with this application. This brings us to the second question of this work. How can we guide the users in their exploration? Since we don't have any exploration logs, we had to use reinforcement learning to develop a guidance system. To the application we've just demonstrated, we added an offline part. So we developed some A3C deep reinforcement learning agents that are interacting with the application in the same way a user would thanks to an environment interface. We trained agents offline for 100 hours by using the application over and over again with a specific objective. What are those training objectives? The data exploration can take multiple forms. Users might want a global exploration of the dataset to discover the content of it in all its variety, or they might want to have a more local exploration by focusing on a given area of the data space. So what we did is we trained multiple agents with different objectives to get different models that will be neural networks since we use deep reinforcement learning, which will be used to suggest exploration actions to the users. Each model provides a different exploration strategy for a given exploration scenario. To define these training objectives, the first aspect of the training we worked on is the reward computation. In reinforcement learning, the reward defines the incentive leading an agent to achieve a task. So the first type of reward we used in Dora is the familiarity reward, which consists in rewarding the agent when it finds some predefined target items. So this is the usual type of reward that has been used in most of the previous works on reinforcement learning applied to exploratory data analysis. With this type of reward, each target item represents a kind of milestone in the data, and the agent learns the fastest track to join all these items. Familiarity is a very efficient way to develop some exploration strategies, but it is inherently limited by the knowledge of the person defining the target set. To alleviate this problem, we decided to use curiosity reward, which consists in rewarding the agent when it ventures into unexplored states. So curiosity reward has been developed recently by the reinforcement learning community and has had some successful application to games. Our idea is that by mixing familiarity with curiosity, the agents will tend to be more adventurous and to provide a wider exploration of the data space. The second aspect of the training that we worked on to define these objectives is the definition of the target sets. The target set is the set of items the agent is looking for to get the familiarity reward. So the first target set we defined is what we called the scattered set, which is composed of diverse items scattered all over the dataset, resulting in global exploration strategies. For the scattered set, we used the resulting classification from the Galaxy Zoo project, and we sampled each of its 1500 classes of galaxies to build the target set. In opposition to this scattered set, we developed what we called the concentrated set, which is composed of similar items sharing the same area in the dataset, which results in more local exploration strategies. For the concentrated set, we picked at each episode of the training a different class of the Galaxy Zoo results and trained the agents only on these galaxies. So to summarize, the idea behind the training of all these different agents with all these different exploration strategies is that as their needs evolve during their exploration sessions, the users can optimize their guidance by always selecting the most suited model. So in Dora, the user interaction consists in opportunistic model and operator selections. Let's see what it means in action. So to begin with, we have to select an exploration mode. We offer 3 different exploration modes. In the manual mode, the user does not receive any kind of guidance. In the partially guided mode, the model suggests the operator to execute, selects the input set and the attributes of the operator, but the user can decide to ignore the suggestion. In the fully guided mode, the model decides every aspect of the exploration and the user can only start or stop the exploration. Let's start with the partially guided mode. The second aspect of the guidance we have to select is the model that will be used for the guidance. So the user has to select the target set that was used for the training of the model between the scattered or concentrated target set and the weight that was used for the curiosity reward during the training of the model. It's a value between 0 and 1. So let's start with the simple scattered target set and no curiosity model. So let's execute the first operator. So here we see that the item set that was selected by the model is an item set composed of very dim and dark galaxies. So we are more interested into bright galaxies. So we will change the exploration to that, and we can also decide to do the first facet on the redshift, let's say. Let's execute it. So now we are pretty happy with the selection of the model, and since the objective is mostly to show you how the guidance works, we can shift the exploration mode to fully guided and let the model decide the exploration. So we start the exploration. And now at each step we see that the model picks the input set and the next operation. Now at any time, the user can stop the exploration and decide to change the model that's used for guidance. Let's pick one with a little curiosity. We decide to load the model, and we see that the input set and the next operation that was picked by this model is different from the ones from the previous model. At any time, a user can also look under the hood and see the training information of the model it's been using for guidance. Here we see the level of familiarity and curiosity that was obtained by the model during the training and the global rewards. We can also see the strategy that was developed by the model during the training, as we can see the types of operators that was picked by the model. So let's go back to the application, and let's start the exploration with this model. So here the models are pretty close. There's very little difference in their training, so their strategies are quite similar. Here we have interesting galaxies that are cigar-shaped. Those are spiral galaxies that are seen from the side, so they look like lines. So we can decide to have a local exploration of this area by picking the concentrated target set. We load the set, and we start the exploration again. So due to the way the model was trained with a concentrated target set and change of target set at each episode, these models are looking for similar galaxies in the surroundings of the local exploration area. We can notice that this model is making a much heavier use of a binary operator, allowing a gradual exploration of the surroundings. Now we can decide we have seen enough on this local exploration and go back to the scattered exploration. We will also add a little more curiosity to get an even more adventurous exploration. Here in the current pipeline area, you can see for each operator that has been executed, the level of familiarity and curiosity that was obtained by this operation. You can see here that this step of exploration brought a lot of familiarity reward, since many of these items showed of interest for us and were probably in the classification from the Galaxy Zoo. This was the demonstration of Dora the Explorer. If you're interested in more information, we have published another paper at the AIDM workshop of the SIGMOD 2021 conference, which is called Balancing Familiarity and Curiosity in Data Exploration with Deep Reinforcement Learning. In this paper, we are focusing more on the training of the different models, on the impact of the operators, and on the balance of familiarity and curiosity. And we had quite a few interesting results, as the fact that although it's working for games, curiosity by itself does not really work for exploratory data analysis, but that the best performing models were the ones with a little amount of curiosity. We have quite a few possible future works, like the scaling and to change the nature of the data we explore, to exploit the user feedback to optimize the guidance, and to study alternative reward methods that are not limited, like familiarity, to the actual knowledge of the dataset we explore. So Dora the Explorer is available online, and you can get the code freely on GitHub. Thank you for listening.